Okay, so let us start with the usual setting. We have a transformation f from m to m, measurable transformation. And we have a probability measure invariant under F. And I'm going to suppose that we have a sequence of functions, say phi n from m to r, is of measurable functions. Is called subadditive if it satisfies the following relation: phi of m plus n of x is less or equal than phi m fn of x plus phi n of x. So this is a property of the sequence with respect to the data. The function, the transformation f is involved here. So this should be true for every m n integers and mu almost every x. When I say that something is true for mu almost every x, I mean that the set of points that do not satisfy this condition has zero measure. Okay? Examples. Suppose we are given a function, a unique function phi from m to r. Given one function, we can define phi n of x to be phi of x plus phi f of x, etc., phi f n minus 1 of x. So phi n, this is sometimes called, also represented, this is just notation, just represented as the sum of phi over the first n iterates of x. It's just notation. You take this, you calculate the function on the first n iterates of a given point, and you call that sum phi n of x. Okay? Then, with this definition, phi m plus n of x is phi of x, etc., phi fn minus 1 minus 1 of x. Then you go on, phi fn of x right? That's by definition. And then you look at this sum, and you see that it can be written as the sum of two expressions. this one and this one. This one is just phi n of x. And the second one has, so this has n terms, right? And this one has m terms. This is just phi m, but not of x, because you start adding on, you start counting on this point, fn of x. This is the sum of phi over the first m iterates of the point fn. Okay? So the conclusion is that we have something like this, except that we have better than, less or equal than. We actually have equal. Here we have equal. Of course, that's a special case. So in this case, we say subadditive, and then in this special case, we say that the sequence is actually additive. But additive is a special case of subadditive. Okay? So whatever I'm going to say for such a sequence applies in particular for this choice. The second example, instead of looking for a function from m to r, I'm going to consider a function from m to the linear group. Okay? And then I'm going to define phi n of x to be the logarithm of the norm of an. Okay. Let me remind you that whenever I speak of norm, the norm of a matrix is, by definition, the operator norm, which is the supremum of b applied to v divided by v for every v different from 0. Okay? So this norm has the following property. If I multiply two matrices, say B times C, this is, okay. So this norm has the following property. Yeah. Okay. So exercise immediate from the definition. This norm has this property. The norm of a product is less or equal than the product of the norms. Okay? This is immediate from this definition. Then, if I write phi m plus n of x is the logarithm of a m plus n of x. Now, by definition of this, that means the product a of x, a f of x, a f n minus 1 of x, a f n of x, a f m plus n minus 1 of x. Okay? That's what this means. And again, that's very similar to what is written there. This here is an of x, and this is am of fn of x. So phi m plus n of x is the logarithm of a m f n of x times a n of x norm. Right? And because of this relation, that is less or equal than the sum of the two logarithms. Okay? So this sequence is also subadditive. And this time, in general, this inequality is strict, and so this one may be strict as well. Are there any questions? I'm going to state a theorem about subadditive sequences, and then as immediate corollaries we will get a theorem about additive sequences and a theorem about linear cocycles. That's the idea, because of these two examples. Now I need one more notation. Given a function phi from M to R, we call the positive part of phi is the function phi plus, defined as follows. Phi plus is the maximum between phi and 0. The negative part of phi is the minimum between phi and 0. And then we have two nice relations. One relation says that phi is phi plus phi minus. And the other relation is that the absolute value of phi is phi plus minus phi minus. Okay. Well, actually, that's not the way I wrote it in the book. So let me change the definitions here. So the way I wrote it, this is the maximum between minus phi and 0. And then this is okay. Just change the sign in phi minus. Okay, so the result that I'm going to prove in the next today and on Thursday is the subadditive ergodic theorem, which was proven by a British mathematician called Kingman, John Kingman. It says, let phi n be a subadditive sequence such that the positive part of phi1 is integrable, is an integrable function. measure mu. For the measure mu. With respect to the measure mu. Then the limit 1 over n phi n of x exists for mu almost every point. Limit exists for mu almost every point. Let's give it a name, phi of x. There's only one little thing that I have to say, is that it can be minus infinity. I don't want to give that too much importance, but when I say it exists in real or in the real numbers, or it's either a real number or minus infinity. Moreover, phi is integrable with respect to mu. Phi is an invariant function. I think I already defined this, but what this means is that phi is constant on orbits. And C, well, part A says that phi is integrable. We can give, we have a formula for the integral. That's what C is. The integral of phi is the limit 1 over n integral of phi n. Part C is very easy to remember. You just go here to this quality and you take integrals in the right places. That's something that you cannot do without a proof, but well, one can prove. Okay? But this is the sub-additive ergodic theorem that we are going to prove. Let me, before we prove that, let me tell you what are the consequences. There are two very important consequences. Wait, sorry. Yes, sorry. Phi plus is integrable. Thank you. This limit can be minus infinity. Okay. So as I said, this is a general theorem for any subadditive sequence. But if you make special choices, like this one, you get a corollary that is called the ergodic theorem of Birkhoff. What does the ergodic theorem say? Let phi be an integrable function with respect to mu, then I'm just going to write this down in the special case where phi n is given by that formula. Then well, let's give this a different name, phi twiddle. Then phi twiddle x limits 1 over n phi of x exists almost everywhere. Phi twiddle is integrable. Phi twiddle is invariant. And corresponding to part C, the integral of phi twiddle is equal to the integral of phi. So the ergodic theorem of Birkhoff is an immediate corollary of the subadditive ergodic theorem. It's a special case applied to this kind of sequences. Unfortunately, most proofs of the subadditive ergodic theorem use the ergodic theorem. So you cannot conclude the ergodic theorem as a corollary if you use it. But the proof I'm going to give does not use the ergodic theorem. So what I'm doing is honest. The other corollary corresponding to this case is the theorem of Furstenberg. Furstenberg-Keston. Saying that so let A be such that I want the first function phi1 plus to be integrable, so such that log plus of A is integrable. The function is integrable with respect to mu. Then, and it's again the same statement, just for that special case. Then this limit 1 over n log of a n of x exists mu almost everywhere. And this time I'm not going to call the limit phi twiddle because I already invented a name for it. I call it lambda plus of x. Okay. Moreover, we have that lambda plus is integrable. Lambda plus is invariant. And the integral of lambda plus is the limit 1 over n integral of the logarithm of an. Corresponding exactly to the three statements here. Okay. So once again, the theorem of Kingman contains the theorem of Furstenberg-Keston as a special case. I want to make, before we go into the proof, I want to make some observations, more or less simple. The first one has to do with this assumption here. With this assumption that phi 1 plus is integrable. You see, if phi n is subadditive, phi n of x is less or equal than what? N is n minus 1 plus 1, right? So if I use this, I get that phi n of x is less than phi n minus 1 of x plus phi f n minus 1 phi 1 of x. Okay? And now I can play the same game again. Here, I repeat this observation, and I get that this is less than phi n minus 2 of x plus phi 1 f n minus 2 of x plus phi 1 of f n minus 1 of x. All right? And now I do this n times, and I conclude that phi n of x is less than phi 1 of x plus phi 1 of f of x, phi 1 of f n minus 2 of x, phi 1 of f n minus 1 of x. Okay? I'm doing this very simple calculation too because it's going to be used in the proof, but also to give you time to getting used to this notion. So you see, phi plus, the positive part, is either the function or 0, depending on what is biggest. So it's immediate from the definition that this implies that phi n plus is less or equal than phi1 plus phi1 plus of x Okay? And this implies that the integral of phi n plus is less or equal than the sums of all those integrals here the function that we have is phi1 plus. Here we have phi1 composed with f. Okay. Now, we are assuming, I already raised it, we are assuming that the measure mu is invariant under F. And that is the same as saying that the integral, so mu invariant under F is equivalent to saying that the integral of C composed with F is equal to the integral of C for any function, for any integrable function. It's just another way of, I mean, there's something this is a little lemma that has to be proven, but it's true. So all these expressions here I can rewrite as integral of phi1 plus, I can take the f out, integral of phi1, and here also by using this formula n minus 1 times phi1 plus. Okay? So what I've shown is that the integral of phi n plus d mu is less or equal than n times the integral of phi1 plus d mu. So, if phi1 plus is integrable, then phi n plus is integrable for all n. Okay? If the integral of phi1 plus is finite, then this is finite as well. This is just to explain why suddenly phi1 is isolated in the statement. We need the assumption for every n, but we don't have to write it for every n, because if we do it for one, it automatically follows for the other ones. Any questions? Okay. Another observation is that it has to do with the theorem of Furstenberg and Keston. the conorm, remember that I defined the conorm of a matrix to be the infimum over V different from 0. And then I observed that this is the same thing as the inverse of the norm of the inverse. Okay. Now the conorm doesn't have the property of the norm. It has the property the other way around. M of A times B is bigger or equal than M of A, M of B. The norm had the inequality the other way around. And so the functions, if I define Cn of x, as I did here, imitating this, if I define Cn of x to be the logarithm of the conorm, by the way, this is immediate. You know that the norm is submultiplicative, then you use this expression and you get the conorm is supermultiplicative by using the formula. So this sequence here, if I define phi n, the Cn the way I define it phi n, but using the conorm instead, then this sequence is not subadditive, is superadditive. Well, I didn't define superadditive sequences, but it's clear what that means. Cn plus m plus n of x is bigger or equal than Cm of fn of x plus Cn of x. But we don't need a superadditive ergodic theorem, because whenever we have a superadditive sequence, we can construct a subadditive sequence just by taking the symmetric. The sequence minus Cn is subadditive. Okay, just change the sign, and you reduce the superadditive case to the subadditive case just by changing the sign. So using this observation, we can get a second part of the theorem of Furstenberg. We can get a second part that goes as follows. I'm going to write it down completely just for clearness. Be such that I'm not going to write that down yet. I mean, I have to write the assumption corresponding to this, but I'm going to do that at the end. Is integrable with respect to mu. Then lambda minus of x of the logarithm of the conorm exists mu almost everywhere. And lambda minus minus is integrable. Lambda minus is invariant. And condition C, the integral of lambda minus d mu is the limit 1 over n integral of the logarithm of m a n d mu. So what should we write here? So we have to write the positive part of the first function in our sequence. The positive part of the first function in our sequence. What sequence is that? It's Cn, or no, it's not Cn, it's minus Cn. Because we are going to use the sub-additive ergodic theorem. So minus C1. And what is C1? It's the logarithm of the conorm of A. That's what I should write there. Okay? So in other words, the positive part of minus logarithm of A minus 1 minus 1. Okay? Now, fortunately for us, the logarithm of the inverse is minus the logarithm. So this is the logarithm of A inverse positive part. Okay, and that's what I'm going to write there. Log plus A inverse. Okay, so that also follows from the sub-additive ergodic theorem for this sequence, for this choice of a sequence. And the choice is not arbitrary. It is designed so that the limit is this smallest Lyapunov exponent. Okay? Last observation before we start the proof. For random products of matrices, which was the situation that I considered in the very first lecture, for random products of matrices, F is the shift map on the space of sequences of matrices. I explained this and mu is a Bernoulli measure, is a product measure. I also explained that. This means that mu of, well, it's a product measure that we spoke about, or Bernoulli measure. I explained this in terms of the measures of cylinders. Okay. And it turns out, it's a basic fact, that then the system F mu is ergodic. This is a proposition, a lemma. I'm not going to prove, but of course, in order to understand what I'm saying, you need to know what ergodic means. And I'm going to use the easiest definition for me. That is any invariant measure is constant on a full measure subset. So apart from, if you forget zero measure sets, if you ignore zero measure sets, then you may consider any invariant function to be constant. Okay? This is not the usual definition of ergodicity, but it's equivalent. So you may take this as a definition. So the conclusion is, in that case, lambda plus and lambda minus are constants. Always mu almost everywhere. To mu. Full mu measure set. Okay? Oh, sorry. Any invariant function. Sorry. Invariant function is defined here. A function that is constant on orbits. As you iterate, it remains constant. It's constant in time. Then any invariant function is constant, except on the zero measure set. Any function that is constant on orbits, any function that is constant on each orbit, on every orbit, is constant on a full measure set. You may take that as the definition of ergodicity. Okay? And that is the reason why on Monday of the previous week, lambda plus and lambda minus were numbers, and then suddenly they are functions. Is that we started with a situation where those functions were constant, and now we are in a more general situation, and we don't have to work more because this is basic fact. Any invariant function, if the system is ergodic, any invariant function is constant. Okay? So a little bit of history about this theorem. Of course, it was proven by Kingman. I think it's 1963, but I could, sometimes in the 60s. I think it's 1963. Furstenberg-Kesten was before. I think it was 1960 or maybe 1959. Kingman's proof used the ergodic theorem of Birkhoff. The proof that I'm going to give is very recent. It's by Arthur Avila and Jairo Bocchi. What they did was to take they were inspired on a proof of the ergodic theorem of Birkhoff, which was due to Katz-Nelson and Weiss. So this is, as far as I know, the shortest and I would say the only intuitive proof of the ergodic theorem that I know, Katz-Nelson and Weiss. And Arthur and Jair were able to extend it, to extend the proof to the subadditive case without using the ergodic theorem itself. So now, now we have a very, very satisfactory proof of the subadditive ergodic theorem. So let me try to explain how it goes. So we are going to call AN AN will be the integrals of phi n with respect to mu. Okay. And this sequence AN has the following property. I don't think I have to explain. Phi n is subadditive. Okay, let me keep that here. Phi m plus n is less or equal than phi m composed with the fn plus phi n. That's what subadditive means. If you take integrals on both sides of this inequality, you have that am plus n is less or equal than am plus an for every n. Okay? You take integral here, you get am plus n. Integral here, you get an. And here you get am, because this composition with fn is irrelevant because the measure is invariant. Okay? So this is a sequence of real numbers that satisfy this property. We say that an is a subadditive sequence of real numbers. Before I define a subadditive sequence of functions, this is, in fact, a more elementary notion, perhaps one-dimensional sequence of real numbers. Okay. Now, there's a little thing that a little observation that I have to make. Those an are not necessarily real numbers. The integral, since I'm assuming that phi1 plus is integrable, then phi n plus is integrable too. That ensures that the limit exists. It ensures that it cannot be plus infinity, but it could be minus infinity. Okay? So when I say real numbers, I mean or minus infinity. Okay? But observe that this makes sense, even if some of these numbers are minus infinity. Using the usual rules that a real number plus minus infinity is minus infinity. And minus infinity is smaller than anything. Okay? Now, there's a lemma. If an is a subadditive sequence of real numbers or minus infinity, then the limit 1 over n an exists. And this is really the very baby version of the subadditive ergodic theorem. That's where the subadditive ergodic theorem starts. It's this little lemma that the limit exists and is equal to the infimum of 1 over n an. Again, this number is a real number or minus infinity. Okay? This is used throughout the proof. That's the reason, in some sense, the reason why the subadditive ergodic theorem is true. I'm not going to prove it here. This is a calculus exercise. Well, it is proven in the book, so but it's really something that you can give as an exercise in a calculus class. So, what are we going to do with that? We are going to consider this number, L, which is the limit 1 over n an. That is the limit 1 over n integral of phi n d mu. And by the way, the lemma says that the limit is equal to the infimum. Okay. That number is here in the statement. Okay, it's the same expression. It's an important expression. What we are going to try to prove is that before I say it, the main part of the theorem is the first part. We want to prove that this limit exists. Okay? So for that, we are going to consider two numbers, two functions, and be careful. Phi plus x is the limit sup 1 over n phi n of x, and phi minus x is the lim inf. I said be careful. I'm writing plus and minus as subscript. This is not the positive part or the negative part. It's subscript. Okay. So that's no problem. These two things exist. Could be infinite, but they exist. And we are going to prove that, let's see, the right order. We are going to prove that the integral of phi minus is bigger or equal than L. And we will also prove that phi plus, the integral of phi plus, is less or equal than L. Now observe, suppose we know this, okay? We also have, it's obvious that phi minus is less or equal of x, is less or equal than phi plus for all x. Right? So we have two functions. One is always smaller than the other. But the integral of the smaller is bigger than the integral of the larger. This, together with A and B, implies the only way these three inequalities can coexist is if the functions are equal. For almost every point. Okay? So these three observations, I mean these two facts, and this simple observation, imply that the two functions, phi minus and phi plus, are equal, which is another way of saying that the limit exists. So phi twiddle exists. Okay? And we ought to also get that these three inequalities have to be equalities. So, and the integral of phi twiddle equals integral of phi minus equals the integral of phi plus equals L. Phi twiddle is just the common value of these two, and then these inequalities have to be equalities as well, right? So if we are able to prove these two facts, we prove this, and we also prove C. Okay? By the way, it's an exercise in the book, and it will be an exercise here to check that these two functions, phi plus and phi minus, are invariant functions. Okay, so phi twiddle is an invariant function. Okay, we will see a few more details later on, but this is the plan of campaign for the proof of the sub-additive ergodic theorem to get these two inequalities here. Let me write that down here. A(n) is integral of phi n d mu. L is the limit 1 of a(n) over n, and we want to prove that the integral of phi minus is bigger or equal than L. The integral of phi plus is less or equal than L. Okay? This is what we have to prove. Okay, the proof would be simpler if we somehow avoided the minus infinity case. I mean, we pay because of this generality that we let these functions, that we only assume phi1 plus to be integrable. If we assume that phi1 plus and phi1 minus are integrable, then the proof becomes simpler. Then in that case, the numbers are finite, are really finite, minus infinity is excluded, and L is finite. In this case, L is again minus infinity plus infinity. But anyway, there are good reasons to keep it general, and I will do that. But for the time being, for now, let us assume that phi minus is finite. Is not minus infinity. Okay? For the time being, let us assume this. We're not going to start with a whole technical case. We're going to suppose that the observe that phi plus. Well, anyway, I'm going to assume this. Then, of course, I have to remove that assumption. Now, we have a lemma. The lemma is the heart of the proof, and I think I can do it today, so I will try to do that. And then the rest of the proof is much softer. This is really the more complicated part of the proof. Let's try to do it today. Fix epsilon and define EK to be the set of points x in M such that phi j of x is less than j phi minus x plus epsilon for some j from 1 to k. So it is important that we understand what this set EK here is. Let me try to explain. Phi minus of x is the lim-inf as n goes to infinity of phi n of x over n. Right? Okay, that's the way I defined it here. This means that there exists some subsequence Ni such that phi Ni of x divided by Ni, so then there exists some subsequence converging to phi minus of x. This is what lim inf means. You have phi minus of x here. Okay, and then there is some subsequence of values of this sequence here converging to phi minus. And moreover, phi minus is the smallest number with this property, is the smallest accumulation point for the sequence. Okay? Now, this means given any epsilon, the sequence, the value of phi Ni of x divided by Ni is less than phi minus x plus epsilon for large Ni. The sequence is accumulating on phi n of x, phi minus of x, and so it is smaller than phi minus of x plus epsilon if Ni is large. Okay? So for each point x, you can find some moment where the sequence phi n of x divided by n is smaller than this number. Ek is the set of points for which that happens before time k. Okay? Maybe it's easier to understand if you divide by j, you move j here. So Ek is a set of points such that phi, so Ek is a set of x such that phi n of x divided by n is less than phi minus of x plus epsilon for some n less or equal than k. The k measures somehow how long it takes for this thing to happen. Okay? So if that is okay, if that is understood, there are two properties that should be clear. Ek is contained in Ek plus 1. This is the set of points for which this phenomenon happens at most at time k. If you give yourself one more time, then of course you get a bigger set. And the other condition, the other property, is that the union of Ek over all k, it's an increasing union, is everything. By definition of lim inf, if phi minus is the lim inf, then there is some subsequence like this, though this will happen for large Ni. So it may be that you have to take a very big k, but for some k, this will have to happen. Is everything okay so far? Let ck of x be phi minus of x plus epsilon if x is in ek, and be phi 1 of x if x is not in ek. Observation. Ck of x is bigger or equal than phi minus of x plus epsilon for every x. Now, why is that? Why is that? There are two cases. There are two cases. If x is in ek, then by definition they are equal. So this case is fine. If x is not in ek, now what does it mean that x is not in ek? It means that this never happens. Okay? And this means that phi j or phi n of x divided by j is bigger or equal than phi minus x plus epsilon for every j from 1 to k. Right? In particular, for j equals 1, what this says is that phi 1 of x is bigger or equal than phi minus of x plus epsilon. Okay, and that's ck in this case. Okay, so let me move that here. So ek is contained in ek plus 1. The union of these ek's is everything. And phi ck is bigger or equal than phi minus x plus epsilon for every epsilon, for every x. the lemma says, the main lemma says, for any n bigger than k, bigger than 1, and mu almost every x. Now I'm going to write a very unpleasant formula, which is more easily understood once you have given the proof. So I ask for patience, because the formula doesn't look nice. Phi n of x is less or equal than the sum I from 0 to n minus k minus 1 of ck fi of x plus the sum I from n minus k to n minus 1 maximum between ck and phi 1 of fi of x. Why would we, why is it useful to have such a formula? We will see that next time on Thursday. But essentially, the main part of the formula is this one, this first term here, which is a sum of the function ck on the first iterates of x. This is like a sum in the ergodic theorem of Birkhoff. And this is a remainder term that we are going to say we can ignore. This is going to be ignored. But that will be done next time. Right now, what we'll try to do is to prove this. And from my point of view, it's much easier to understand the formula once you have the proof. That's not always the case, but in this case, that's true. So here's what we are going to do. And that strategy really comes from Katz-Nelson-Weiss already. We are going to look at the orbit of x, and we are going to consider different moments in the orbits. Proof of the lemma. Take x in M. I wrote here as an exercise that the functions phi plus and phi minus are invariant. So since phi minus is invariant, we have that phi minus of f j of x equals phi minus of x for all j. Okay, keep this in mind. Phi minus is an invariant function. It is constant on orbits. And we are going to look at time and decompose time in a convenient way. So I start at time 0. And I'm going to define m0 to be this first time 0. Okay. Now I'm going to find another time. So this is m0. I'm going to find a time n1 bigger than m0, defined in the following way. This will be the first time that the orbit of x goes inside this set. So n1 is the smallest value of n such that Fn of x goes inside Ek. Well, it may never happen. It may never happen. And in that case, n1 is infinity. Okay? It may happen at time 0. For instance, if x is in Ek, this will happen at time 0. So n1 is n1 bigger or equal than m0. So, yeah, it could be. I'm going to say it this way. The smallest number bigger or equal than m0 such that, okay? So you may think of this as a very bad period in the life of the point x. It wants to get inside Ek, but it takes some time before that happens. And then once it hits Ek here, by definition of Ek, there exists some number j such that this happens. Okay? So then there exists some number j0 from 1 to k such that phi j of x divided by j is smaller than phi minus x plus epsilon. Okay? j0, j1. Okay? So there is some time here, and I'm going to mark it like this. This is j1 iterates. Okay? I mean, there could be more than one j1. You choose the smallest. It doesn't matter. Any one. All right. Are there any questions? That's what's written here. No, it's not what's written here. The point that got inside is not k. It's fn1. It's not x. It's fn1 of x. Okay, thank you. And yes, sure. Here too, right? Except that it doesn't matter because phi minus is an invariant function. Okay, so this is phi minus of x plus epsilon. Okay, so I mark here this picture, j1 iterates, and I look at the end of this time. This is the good period in the life of x. It is enjoying the benefits of Ek. But all things good come to an end, and this is the end. Okay? And then the poor point x goes back to trying to go back to Ek. So it will remain outside Ek for a little while, and then at some point, maybe, some point n2, it will go back to Ek. So what is n2? N2 is the smallest value of n after m1 such that n of x is in ek. Okay? And so on and so forth. Then there's a time j2, etc. This is the key construction. The formula there will be a consequence of our organizing the trajectory in this way. Okay? Somewhere around here is n, and I will stop there. So let's suppose that we go to ns, then we have a js, and then we have a ms, and that's it. Okay? We repeat this until we get ns, js, ms. Okay? Now, let me show you why the formula, how the formula comes from that organization of the trajectory. What does the formula say here? Well, phi n of x by subadditivity phi n of x is less or equal than, let's see, phi n1 of x, this block here, plus phi j1 of f n1 of x, this block here. Well, I will write it like this: phi m1 minus plus phi n2 minus n1 minus m1 of phi m1 of x plus phi m2 minus n2 of phi of f n2 of x, etc. Phi plus phi ms minus ns of f ns of x, and then there's the rest here. Okay, so I divide the trajectory of x into good moments and bad moments and good moments. Now I use subadditivity to try to get to this formula here. Okay, there are two kinds of, three types of terms here. The bad ones that I've written here, the ones where the point is not in EK, not in EK. And the good ones that come from having reached EK. Well, I mean, I'm calling them good and bad. Depends on the point of view. Okay. Now let's see what we can say about each one of them. Let's see what we can say about the bad ones. Well, it is perhaps easiest to say what we can to see what we can say about the good ones, because the good ones, these ones here, m1 minus n1 is just j1, m2 minus n2 is just j2, etc. ms minus ns is js, where these j's come from the definition of ek. Okay? So by the definition of ek, phi m1 minus n1 of f n1 of x is less or equal than m1 minus n1 phi minus of x plus epsilon. Right? Again, it's not phi minus of x. It's phi minus of f n1 of x, but I don't care. Phi m2 minus n2 of f n2 of x is less or equal than m2 minus n2 phi minus of x. With a parenthesis here. Okay. So you see we have upper bounds for these terms, and the upper bounds involve phi minus x of epsilon. Right? And phi minus x plus epsilon is related to ck. So we are going the right way to get an upper bound of phi n in terms of ck. Okay? We are not there yet, but we are going to get there. Now, what about phi n1? We have to use the fact that, yeah, we have to use, okay. What about phi n1 of x? Well, phi n1 of x is less or equal, and I did this calculation before, is less or equal than phi 1 of x plus phi 1 of f n1 minus 1 of x, just by subadditivity. We did this before. And that's this very crude estimate that we are going to use. Phi n2 minus m1 of x is less or equal than phi 1 of f m1 of x plus phi 1 of f n1 minus n2 minus 1 of x, and so on. And that includes the very last bit here. Phi n minus ms of x is less than phi 1 f m of x plus phi 1 of f n minus 1 of x. Okay? So just sub-additivity. I hope I wrote the exponents correctly. No, we are very close to the end of the proof, really. Let's look at this here. This is phi 1 calculated during these iterates. Okay? During these iterates, our point is not in EK. If it's not in EK, outside of EK, phi 1 is the same thing as psi k. So this sum is equal to the sum of psi k fi of x I from 0 to n1 minus 1. For the same reason, this sum here is a sum from time m1 to time n2 when the orbit is outside EK. So this is the sum of psi k fi of x I from m1 to n2 minus 1, and so on and so forth. During the time we are outside, psi k is equal to phi 1. So it's just the same expression. This is good because I want to obtain an estimate with psi k on here. Very well. So now we have to come here and try to relate this to psi k. So well, it says here that phi minus of x plus epsilon is less than psi k. So I could come here and write that this is less or equal than m1 minus n1 times psi k of x. That I can do. But it's not very good for what I want, because I want to get a sum of psi k on the various, on different iterates x. I don't want to have a bunch of psi k's on the point x. Okay? So what am I going to do about that? What I'm going to do is to rewrite this as follows. Equal. Let's see if you agree with me. Equal phi minus x plus epsilon plus phi minus f of x plus epsilon plus phi minus of fn1 minus 1 of x plus epsilon. Okay? All these terms are equal because phi minus is an invariant function. Right? How many terms I have here? M1 minus N1. N1. But here too. No, not this. M1 minus N1 minus 1. I have to have exactly the same number of terms. But this is looks like a silly thing to do because these numbers are all equal. But it's a clever thing to do because now I can use this inequality here at the right points. This is less than ck of x plus ck. Sorry, this is not really what I want. It's not wrong, but it's not what I want. I want here fn1 of x. Here I want n1 plus 1. And here I want m1 minus 1. It doesn't matter. The numbers are the same, but the iterates where I want this to happen are these ones. So now I can say that this is less than ck on fn1 of x plus ck on fn1 plus 1 of x plus ck on fm1 minus 1 of x. In other words, sum of ck fi of x when I goes from n1 to m1 minus 1. Okay? And for the same reason here, same trick, less than the sum of ck fi of x when I goes from n2 to m2 minus 1, etc. And here is the sum from ns to ms minus 1 ck of fi of x. Any questions? Adding these inequalities, first of all, adding the left-hand sides by subadditivity gives us an upper bound for phi n of x. Okay? The left-hand sides, the sum of the left-hand sides is bigger or equal than fn of x. And now let's look at the right-hand sides. What do we have? We have the sum of ck from 0 to n1 minus 1. Then we have the sum of ck from n1 to m1 minus 1. Then from m1 to n2 minus 1. Then from n2 to m2 minus 1, and so on. We have the sums of ck's on these intervals, very carefully arranged, so that in the end we get this. By adding it all up, right? And then someone came up with the observation that this is less than the sum from 0 to n minus k minus 1 of ck. And then you have to look at the other k terms that are not the last k terms. And in the last k terms, for some reason, instead of ck, you write the maximum between ck and phi1 cannot be bad. Okay. What I'm doing here is that in the last k terms, I'm replacing ck by something which is bigger, so it's okay. Of course, it's a very twisted thing to do, because the formula was beautiful before I did that, and now it's awful. But it's at least legal to do that. Okay? Now, of course, I have to explain why anyone would do such a twisted thing. And the reason is that I didn't prove the whole lemma. I proved one case, and there are two cases. This, that I think you can remember in a week from now, you will still remember the proof, I hope, is cleaner than the other case. And the difference is here in the picture. There is a second case that looks like this. When you start doing this, exactly the same thing. It might just happen that the picture is like this. Okay? It might happen that this good period goes beyond n. And then you have to adjust the calculation slightly. And how do you do that? How do you adjust? You use the observation that, well, you don't know anything about these terms here, because the definition of EK only tells you that there is some J that is nice, but in between you don't know anything. You use, in that case, use the observation that this JS is smaller than K. Because it is smaller than K. Because by definition of EK, it is smaller than K. So these last terms here that you don't know anything about are at least a small number of terms. And they can be bounded by this expression. Okay? And that's why we need this ugly term. Otherwise, the calculation is just the same, and it is written down, so I'm not going to repeat it here. But that's the reason why in the statement, for the first case, we could well end with this. We could stop here. But for the second case, there's something more ugly that we have to do, and that's it. Okay? So this is the technical part of the proof of the subadditive ergodic theorem. On Thursday, I will use this to get the statement.